So for tutorial 9, mass transfer using MATLAB, write a general MATLAB function to calculate first to fourth order derivatives of a series of data presented numerically in a matrix whose columns represent vectors of dependent variable. The user should be able to choose between backward, forward, or central differentiation as well as the order of the truncation error. Apply this function to calculate the solid's volume fraction in a riser of a bench scale gas-solid fluidized bed whose axial pressure profile is given in Table 1. Assume fully developed solid flow in the riser and neglect wall shear and solid stress. The densities of the gas and solid phases are 1.2 kg per meter cube and 2,650 kg per meter cube respectively. Okay, so you're given the momentum balance equation for the two-phase flow, in which we find that the pressure drop in the above-mentioned condition is balanced by the weight of the bed, that is equation 1, where P is the pressure, Z is the axial position, rho G and rho S are the gas and solid densities, respectively. Epsilon S is the volume fraction of the solids, and G is the gravitational acceleration. Equation 1 can be solved for the epsilon S here with equation 2 over here. Okay, so the solid's volume fraction profile can be calculated from equation 2 as mentioned once the pressure gradient is extracted from the data tabulated in Table 1. Okay, so we'll look at the program itself. So this program, example 4_2, which has been uploaded, okay, solves for example 4.2, and it calculates and plots the volume fraction profile in the gas-solid fluidized bed. The program uses the function derive to obtain the pressure gradient. Okay, so over here is input data that we have to input to the program. Okay, so P is the vector of the pressures, dz is the axial distance between the pressure probes, and rho G is the density of the gas, and rho S is the density of the solids, where G is 9.81. Okay, so the pressure gradient is dP, such, and we will use derive over here, and the solid's concentration is such, which was the equation given in equation 2. Okay, then we will plot the results, okay, in which the X label will be labeled as Z, and the Y label will be labeled as the solid's volume fraction. Okay, so we will plot Z as the X and Y as the solid volume fraction, which is 100 multiplied by the epsilon itself. Okay, because it is in percentage. Okay, so this one is your derive function. Okay, so the derive function actually differentiates a matrix of data numerically, and derive y calculates the central difference of each vector of matrix y. So derive yh calculated the first order derivative of y by central finite differences using h as the independent variable interval. Okay, so dy is derive yh order method and ERR, which returns the derivative of columns of the matrix Y, where H is the independent variable interval. Okay, order is the order of differentiation up to fourth order, because we are asked to do 1 to fourth order. Okay, method is the finite difference between the method used, which is the backward, central, and forward finite differences. So -1 is for backward, 0 is for central, and 1 for forward finite differences. ERR is the order of error of calculation, where ERR may be 1 or 2 for backward and forward finite difference, and 2 or 4 for central finite differences. Okay, so we will input it to MATLAB. So after you download your M file, please save it to your documents, into your MATLAB file in your documents over here. So we'll click on this. Right. Okay, so we click back to here and we will click Run. And we will be asked to input the data, which is the vector of the pressure. And the vector of the pressure, let's have a look. What is the vector of the pressure again? Okay, so this is the vector of the pressure that we will have to input in, which is 1.8. Okay, we have to put this over here. 1.8, 1.38, 1.09, 0.63, and 0.18. Okay, so we have to, because this is a vector, so I have to input this. And the axial distance of the pressure prop is 0.5 meters apart each. And the density of the gas is 1.2. And the density of the solid is 2650. Okay, and the average solid concentration is given to be 3.26%. Okay, now we should see a figure showing up here. So figure 1 shows the results graphically over here as such, and it can be seen from this figure that the solid's fraction does not change appreciably with weight, and the value of epsilon s varies between about 2.7 to 3.8, okay, approximately, with its mean value. Okay, so you can point it over here to obtain the solid volume fraction, okay, and with its mean value of 3.26%. So this confirms the assumption made at the beginning that the measurements are done in the fully developed zone where the solids move at a constant velocity. Okay, so that's pretty much for tutorial over here. Thank you.